Okay, welcome back to Essential Perturbation Theory and Asymptotic Analysis. I had a couple of questions in before class got started. I tried to answer some of them. Are there any other questions besides those? Okay. So the subject of today's lecture is to finish the linear non-constant coefficient boundary value problem that we started with last time. There we ended with getting a composite solution of order 1, 1. And now we're going to carry that a little bit farther and try to get the composite solution of order 2, 2, and then compare these two things together. And in this case, we can compute a numerical solution for the problem at hand, and we'll compare that to the numerical solution and call that the true solution. So let's go back. And here's the problem that we're solving. It's a second order linear non-constant coefficient ODE. It's singularly perturbed. There's an epsilon multiplying the highest order term. Of course, if epsilon is equal to 0, that's kind of the limiting case. Then we get a first order ODE and two boundary conditions, and so that's why we call it singular perturbation problem. It can't satisfy both boundary conditions if it's a first order problem. So it's this problem we constructed a 1, 1 composite solution. We knew from theory that the boundary layer existed at the left-hand endpoint, which in this case is x0, and that's because our p function, the function multiplying the first order derivative, is a positive function on the entire interval of interest, the domain of interest 0 to 1. So we have a boundary layer at the left-hand endpoint. The boundary layer thickness, moreover, we know from a previous result, I think I called that a proposition, is epsilon. So delta is fixed at epsilon. We know that much already from the previous theories. We don't have to figure out where the boundary layer is. We don't have to figure out what the boundary layer thickness should be. We know already how to do that. So in the last example, we computed the 1, 1 composite solution. And that was here. So let me remind you of the usual approach. You use the expansion of the outer problem up to the first order term, and the expansion of the inner solution approximation up to first order. And then you subtract from that the matching term up to first order. And we got something which looks like this in the end. And that doesn't mean anything to you, I suppose, except that we plotted this out and it looked like a pretty good match to our true solution computed numerically. So the point of the rest of this exercise, or the next exercise, I should say, next example, is to compute the composite solution of order 2. So we already have the inner expansion up to 2 terms. Well, 3 terms if you count the following way: leading order, first order correction, and second order correction. So 3 terms. We have the same for the inner solution expansion. We have 3 terms: leading order, first order correction, second order correction. So now we know what the procedure is. We'll go through that a bit more quickly. So let's do the inner matching function of order 2, 2. So the expansion up to order 2, writing in terms of the stretched variable z, is as follows. Well, I'm not going to read off every term. So 0th order or leading order, first order correction, and all of these terms comprise the second order correction. So this is y0, y1, and that's y2. Okay. Notice, as usual, for the inner solution expansion, we have a bunch of asymptotic decay terms. The boundary layer is located at the left-hand endpoint, and that means we're working with z being strictly positive. It's measuring how far we are away from the boundary layer, and we're measuring a positive distance as we move towards the outer solution region. The picture is as follows. So our boundary layer is located here at x equals 0, which is also the same as z equals 0. We have an inner solution region. We have an outer solution region. And then we're going to have some sort of overlapping region. Okay, which kind of goes over the inner solution region and the outer solution region, straddles both sides. And we simply look at where both are active in order to do our matching procedure. It's in this region where we're going to create this new variable w using an intermediate scale called eta. But in any case, in our inner solution problem, z is measuring how far we are away from the boundary layer, and z is going to be positive as we move through the boundary layer towards the outer solution region. So these terms are asymptotically or exponentially decaying here, 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 here. And we have a few other terms which are algebraically growing, but most of the terms of interest are asymptotically decaying. So now if we, according to our procedure, replace the z variable with, what variable did I say to replace that with? Okay, so z is going to get replaced with, kind of eliminated a step in between. All right, so let's remind ourselves that w is, well, how does it work? W is equal to x over eta. Z is equal to x over epsilon. So how do we replace z with w? Well, first of all, we're going to write x is equal to w eta, and that means z is equal to w eta over epsilon. So everywhere we see z, we're going to replace that with the variable w eta over epsilon. And I did that, and then I took any terms which were asymptotically decaying, and I recognized that as I send epsilon to 0, this term, so as we send epsilon to 0, we were getting terms which look like e to the minus z, which is going to be now w eta over epsilon. What's happening? So w is remaining fixed. Eta and epsilon are both going to 0 as epsilon goes to 0, but epsilon is going to 0 faster than eta. So that means that ultimately this is going to plus infinity, which means that this is going to be transcendentally small. And so any transcendentally small terms get replaced with little o of epsilon to the r, eta to the r, just like in the last case. Okay, so every instance of e to the minus z, we replace with order epsilon to the r, little o epsilon to the r over eta to the r, which is something which is going to be extremely small, right? For r large, now eta is going to 0 faster than, sorry, epsilon is going to 0 faster than eta, so this is becoming very, very small. Okay, which is what we mean by transcendentally small. Now, all we have to do is pay attention to what terms are going to survive. We have to collect all the terms which are larger than little o of epsilon squared. So we have to decide what terms are going to survive. There's a bunch of complicated terms here. I'm going to flip to the next page and show you what survives, and then maybe we'll come back and see why they survived. Okay, so my first pass at what survives is all of this stuff here. First pass. So for example, these two terms survive because, well, I have this term and this term comes from here. So 1 minus C0. What about C0 minus 1 times W eta? Where does that come from? That term comes from, we have C1 with a minus sign here. Actually, that goes to the eta term. I'm looking for just C0 minus W eta. So the C0 W eta is going to come from this guy right here. Yeah. Where does the other one come from? From here, right here. Well, this one, see this term here is going to give us a minus W eta. Epsilon kills the epsilon here. So that's where that guy survives from. Okay, and hopefully you can take my take my word for the fact that all of these other terms pop out. But now this is still a bit too many terms, I think. I might want to get rid of a few more. See, is that true? So we have this guy. No, we're keeping this guy. I must have gotten rid of all the terms that I wanted to get rid of already. Yeah, that's so this one I don't have to be. So this one, I was kind of confusing myself, but let me clarify. So in this one, I'm just going to keep all the terms that I think are not going to be transcendentally small. It's in the outer expansion where I'm going to select my eta scale in order to match the number of terms that I'm preserving here. So that's kind of the game I'm playing. So here, I'm throwing away all terms which are transcendentally small and keeping all the rest. And here I'm not setting the scale for eta. It's going to be when I set, or whenever I do the outer expansion. So all I did was kept all terms which are not transcendentally small. And then I kind of simplified a bit here, keeping all terms which are larger than little o of eta squared, sorry, epsilon squared. I look at epsilon and I think eta. I look at eta and I think epsilon. They don't look anything alike, but they start with the same letter in English. So this is just collecting terms. I collect, so what I try to do is I collect powers of eta, powers of epsilon, and mixed powers. So for example, I'm going to collect everything which is order 1, everything which is order eta, that's kind of the next scale, then order epsilon. The next scale I'm going to keep is eta squared. Remember, W is order 1. Then eta epsilon is a bit smaller. Then finally, epsilon squared is the smallest. And everything else I claim goes into the garbage bin of little o of eta squared. That means that if this is true, then everything leading up to this term here is my 2-2 match. That's the 2-2 match function. So all I did here was copy all of these terms down to here. That tells me exactly what terms I'm going to need to match with the inner solution expansion. So this is my target. So is that clear for everyone? That's the target that I'm shooting for. The target that I'm shooting for when I do the outer solution expansion. Now this outer solution expansion up to 2 terms is as follows. This is the leading order, first order correction, second order correction. So in other words, Y0 little y1 and little y2. Now for the outer solution expansion, we already mentioned a couple of binomial expansions that we needed. One was 1 over something to the first power. The other was 1 over something to the third power. And now we need the fifth power as well, because these are the terms that appear for us in the expansion up to second order. Here's the fifth power. We've already have this expansion and this one in a previous slide. So go back and grab those. Binomial expansion says that this expands to this, up to big O of eta cubed. I could write this, by the way, as little o eta squared. Little o of eta squared, big O of eta cubed. I'm essentially discarding, or it's the same waste bin. Now you keep in mind that W is a fixed, finite, order 1 number. W, when you do these expansions, W is treated as a fixed, finite, order 1 number. Now you just do your replacements. This is everywhere I see X, I have to replace, and I got to remind myself what's going on here. Everywhere I see X, I'm going to replace with what? It's going to be, I have to work backwards. I can never work forward. Or I should say I need to work forward rather than backwards. So here's my original way of defining W. And so X is going to be W of eta. Okay, which I guess is why I did this expansion here in particular. So all I'm doing is replacing every instance of X with W eta, and then I'm going to start expanding. This in this time around, I grouped my expansions according to my binomial expansions of 1 over X, 1 over 1 plus X, the first power, and then the cubic and the fifth power. So here's the 1 over 1 plus X, 1 over 1 plus X cubed, 1 over 1 plus X to the fifth. So I grouped them that way. That way I only had to write these expansions 1 time each. Now I'm going to collect terms, and now it's at this point when you use the outer solution expansion where you have to start choosing the scale for eta. I have to start choosing my scale for eta. So let's do, I think I'm going to do a first pass here, and then I'm going to cut that down a bit. So here's my first pass. I'm going to keep order 1 terms, order eta, order epsilon, order eta squared, order eta epsilon, order eta squared, order epsilon terms. And what if I discard it at this point? Well, I've discarded everything which is, let's say, bigger than epsilon squared. So this term multiplied that term is going to be order epsilon squared, little o, as is this term. What about these guys? Well, this is at least epsilon here. So I'm going to, maybe I'll keep some of these and maybe I'll have to discount some others. But I also have terms which look like this, big O of eta cubed. And I'm going to have to make a decision about whether or not I should or should have not kept those terms. Ultimately, I'm going to decide to discard those. And that's going to set the scale for me. Okay, so I'm keeping up to these orders. And the reason I know to keep up these orders is because I know that I have exactly the same terms appearing in my inner expansion. So I've kept epsilon squared eta. Oh, actually, let's go back and look and see if this term appears. I might be wrong about that one. So let's go back and see if this term appears. It's eta squared epsilon. Did we have an eta squared epsilon term there? No, we didn't. We didn't have an eta squared epsilon term there. So we might have to get rid of that. We do have an eta squared term. And we know that we're going to have to match that guy because it's got a coefficient in it. It's got a free parameter in there. But we don't have this term. So how do I get rid of this guy? How do I get rid of that guy? Well, I'm going to say I want this to be little o of epsilon squared, right? So I want this guy to go to 0 as I take the limit epsilon to 0 of eta squared over epsilon divided by epsilon squared. I want that to be 0. That's exactly equal to the limit as epsilon goes to 0 of eta squared over epsilon. Right? So what is that going to do for me? Well, it's going to tell me that I need to set this scale to be a certain something, which we'll get to in a moment. So if I get rid of that guy, that was my eta squared epsilon term, that extra bit. I'm getting rid of that. This just becomes a number, as does this one, and this one I figure out what those numbers are. Now I get this. So here are the choices that I need to make. This one is the one that I just discarded, but I also need to discard any eta cubed terms. I need those to be little o of epsilon squared. Where did those come from? Well, those are all of these terms. Okay, this one is clearly not going to factor, as is this one, but this one could factor because it's getting multiplied by this order 1 term. See that? So that's where that's going. I need that to be little o of epsilon squared. I need to get rid of this one. I need that one to be little o of epsilon squared, but that just means that eta squared over epsilon goes to 0. This latter requirement is the same that we used previously when we did the 1-1 match. And this one is the more restrictive. So let's see what we get with this latter requirement. The latter requirement, this could be satisfied by taking eta of epsilon equals to epsilon to the 2/3 power. Sorry, this is for the latter requirement. I made a mistake. The latter requirement can be satisfied by taking eta to be epsilon to the 2/3. The first requirement is stronger, as you can see, and it can't be satisfied with the same assumption. But it could be satisfied by taking eta to be epsilon to the 3/4 power. So as you can see, what's trending here is that this power, if I think about eta as being epsilon to some power alpha, what's happening as n and m are simultaneously getting larger, this guy is going up to the number 1. It's slowly creeping up to number 1, to the number 1. And it looks like it's doing it in such a way that we had previously, right? So I'm at n equals 2, m equals 2. That's just going to be n plus 1, and this is n plus 2. It looks like my trend is going to be that I need to take alpha to be what? Alpha should be something like n plus 1 over n plus 2. And that, of course, is going to tend towards 1. So if you do the 3-3 match, that's what I'm conjecturing you'll see. You'll see for 3-3, you're going to get 4 over 5. So that's not a proof, that's just a conjecture. All right, so now remember the procedure. I started with the outer or the inner solution. I knew what I needed to match. So I'm only going to keep that many terms in the outer solution. That makes me have to decide on some scale for eta, and that sets the number of terms so that I can match exactly with what I have in the inner solution. So now the outer solution, or the outer match, I call it, is just this. So now let's do matching. For matching, we need to make this function match exactly to this function. This function has a bunch of unknown parameters. Now, these were determined when I did the 1-1 match. And we'll see what happens when we do the 2-2 match, that we get exactly the same parameters coming out, except for the brand new one, which is C2, that will be deduced and will be something new. So there's the 2-2 outer match function. Now we need to set these two things equal to each other to all the appropriate orders. And so as what happened, well, as we saw with the 1-1 match, we get C0 equals -1 when we match the order 1 terms. When we match the order eta terms, same thing. This one just gives the same constant for C0. That's good. No new information, so that's at least consistent. When we match the order epsilon terms, that gives us, again, C1 equals -3/2. That's the same thing that we had when we did the 1-1 match. This new term that pops out is just going to be something which is consistent. That's good. As is this new term order eta epsilon, which again gives us something which is consistent. So I believe both of these two are new and didn't appear in the 1-1 match. And finally, we get something new when we go out to order epsilon squared. By the way, you can look, and by the choice of my scaling, this really is a hierarchy of scales. So this is the smallest scale, this is next smallest, and so on, all the way down. Keeping in mind that epsilon goes to 0 faster than eta. So this scale, or this matching, tells me that C2 is equal to -21/4. That's the new piece of information. Okay, so this tells me what my 2-2 match function should be. It's exactly this. But remember, this is exactly our outer solution match function. It's exactly the same that we have here. Because why is that true? Well, because this can't produce any new information. There are no free parameters. There are nothing new to produce. But it's interesting that it's the inner solution which sets the number of terms in the outer solution. That's the usual process. The number of terms in the inner solution that we need to match sets the number of terms that we're going to expect to see in the outer solution match function. But then when we set those pre-parameters, ultimately, our 2-2 match is exactly the same as the outer match function, which is that. So now we're basically home free. The composite solution is defined as usual. You take the outer solution with its 3 terms, leading order, first order correction, second order correction. And you add to that the inner solution expansion of it with its 3 terms, the leading order, first order correction, and the second order correction. You're going to replace the z variable with x over epsilon. And finally, you have to subtract the match function because that's the function which tells you what are the same terms in both. And since you don't want to double count those, you have to subtract the match function off because it appears in both this and that expansion. You have to replace the w that is natural in that expansion with x over eta. Now, it seems like you might possibly have an eta trailing along, but the way you do things, this eta always gets multiplied away. It always cancels out and it won't be there. Well, trust me, this is a painful procedure. I did this by hand, no computer algebra. And what told me I was on the right track is when I matched it to the 1-1 function, it appeared to be correct. I guess, well, the book by Bender and Orszag, which I referenced several times, that's kind of like the asymptotic and analyst's Bible. Did I say that right? The Asymptotic Analyst's Bible, Bender-Norzag. It's a famous book from 1978. It's still in print and still highly referenced. Had actually the composite 3-3 match. So I could match the first 3 terms up with the first 4 terms that that they computed in their match. Don't think I actually did it that way, but that's one way to do it. In any case, you can see what's happening here. This is the outer solution expansion of 3 terms. This is the inner solution expansion of 3 terms, written in all the appropriate variables. And then this is the matching function that I'm going to subtract off because otherwise I would be double counting. And notice that there are no free parameters. There's no free etas floating around. Okay, even though I never decided the scale for eta, it's not floating around and not going to bother me. I never had to actually fix or choose the scale. I simply said what it could be to make things work out, and I left it at that. So this was actually the hard part. Writing that was not so bad, but doing the simplification. What happens every time is when you look at the match function, it's going to go into the inner solution expansion, and it's going to kill off all of the terms that you see here. -2, minus this one's going to be plus 2x, minus 3/2 epsilon. All of these terms are going to appear somewhere, and eventually you get a full reduction in the number of terms. You really do get a double counting, but the cancellation comes from actual terms which appear in the inner solution expansion. So for example, this guy here becomes 3/2 x to the epsilon. Actually, that one doesn't cancel. Here's one that cancels. This one is going to be -21/4 epsilon squared, and that cancels with this guy. And what about this one? 11/2 x epsilon. I think it's the combination of a couple of different terms which gives that cancellation. I don't see it right off the top of my head. This one, 3/2, that's -3/2 epsilon. That one cancels with the combination of these terms. But anyway, all of these terms, 1, 2, 3, 4, 5, 6 of them get canceled out. So you really do get a full simplification. So when I write this out, this is the 2-2 composite. And I've written it in all kinds of jumbled ways. So all of this stuff here is the outer solution expansion. I didn't modify that in any way. It was only the inner solution expansion that simplified by the death of those common terms with the matching solution. Okay, so that's great. We have 2 composite expansions, a 1-1 and a 2-2. So let's compare them against each other and see what we get. What we would expect, as always, the higher order term should do better than the lower order term. I guess you wouldn't be guaranteed that in analysis. That's not, we only give an error estimate. We never say exactly how close things are. But in this case, the thing you would expect actually happens. The 2-2 expansion in green, which is right in here, is closer to the true solution, which sits on top. That's the exact solution, or the true solution, that what I'm calling the true solution, which was actually computed numerically. Not too hard of a numerical problem, by the way, because this numerical problem is, this problem is linear, so the numericals are linear, and you can solve this pretty straightforwardly. Now, I didn't actually code this up myself. I simply said, Mathematica here, do a D-solve or ND solve, and it did it no problem. Okay, so by the way, at some point I'll share the Mathematica notebook. So if you want to see how these things are done in Mathematica, I'll happily share these things. They're not quite commented up to the degree I would like, but I can certainly share them with you. So the takeaway is for this value of epsilon, which isn't too small, epsilon equals 0.1, the 2-2 composite does better. And I would imagine as epsilon gets smaller, which should we expect? We should expect both of these composite solutions to get very close to the true solution. Okay, very close. That's because this differs from this guy by big O of epsilon, and this differs from this one by big O of epsilon squared. So they're both going to collapse as epsilon gets smaller and smaller. That's really remarkable, actually, because as epsilon gets smaller and smaller, this guy is going to, the blue curve is actually going to converge to something which kind of has a jump discontinuity. As epsilon gets smaller and smaller, it converges non-uniformly to a function, which is essentially this function plus this point value down here, right? It can't be uniformly, it can't be uniform convergence in epsilon because we know that the uniform limit of continuous functions is continuous. The uniform limit of continuous functions has to be continuous, and this uniform limit is not. You always have that point down there and that sort of structure. So in other words, the uniform limit of this guy looks something like that. Okay. Let's solve another problem. Actually, this problem is cooler than the last one. Of course, maybe you didn't think the last one was all that cool, so the bar may not be set so high. And you know, I'm talking fast today for some reason. We might finish a little bit early. So this is the only set of slides that I have. Actually, there's a third slide deck for chapter 5, and that's going to be on nonlinear problems, and I plan to start covering that next time we meet Tuesday. All right, so let's get into this corner layer problem because it is very cool. What do I mean by a corner layer? Well, we'll get there. But let's start by looking at this ODE. See what's happening here. Let me point out some differences from problems that we've solved and looked at previously. So first of all, our domain we're using is a bit different. So normally we're operating from 0 to 1. I just want to show you that you don't have to operate from 0 to 1, no big deal. Here we're going to operate from -1 to 1. And here's the ODE that we want to solve. And here are its boundary conditions. Whenever x is equal to -1, y is going to be 1. Whenever x is equal to 1, y is going to be 2. Okay, so what? No big deal. Now, let's look at the ODE. It's a singular perturbation problem, as usual. It's a linear problem, right? Because the ODE is linear. It's non-constant coefficients. This coefficient is constant, but this middle coefficient is not constant. So what is this saying? This is saying my P of x is equal to x, and my Q of x is equal to -1. Q of x really doesn't come into play when we're discussing the existence and uniqueness of solutions and things like that. Well, actually it does in one case, but not in the other. It definitely doesn't come into consideration when we talk about the location of the boundary layer, or it doesn't seem to so far. What does come into consideration is this function. Remember, we gave a result which said as P is everywhere positive on the interval of interest, then we had a boundary layer at the left-hand endpoint. And we had another result which said if P is everywhere negative, then our boundary layer is at the right-hand endpoint. So what do we do in this case? So in this case, our P has a 0 right in the middle of the domain of interest, -1 to 1. It's 0 whenever x is equal to 0. So what do we do in that case? Well, we had a remark, and the remark said we're probably going to expect to see a boundary layer at the location of that simple 0. So we're expecting to see a boundary layer at x equals 0. So in this case, that's exactly what happens. We have a boundary layer at x equals 0. And there's another way we're going to know this is true. We're going to exhibit an actual analytic solution for this problem. So let's do that next. Before I get into that, though, I want you to be aware of the fact that if x is equal to, sorry, not x, but y, let's suppose y is equal to something like c of x. Yeah, just c of x. What do we get? Well, if y is equal to c of x, what is its second derivative? 0. So this term goes away. Then we have x times the derivative of c of x, which is going to be c. So c times x minus c times x equals 0, right? So that is a solution to this problem. Well, what do we know about second order linear non-constant coefficient problems or linear second order ODEs in general? They must have two linearly independent solutions. So we've found one. So how do we find the other one? Well, there's a technique that you may or may not have heard of called the method of reduction of order. How many of you have heard of that? It's a technique which is taught sometimes in your first ODE course, and sometimes in the second ODE course, and sometimes it's left with the textbooks, the old dusty ones. So in other words, most of you probably have not heard of the method of reduction of order. I'm not going to review it here. I'm simply going to say that's how I got this solution. And I got it by noting that that's one solution. And if you know that if you have a non-constant coefficient linear second order equation, you find one, you can easily find the other using this method. Okay, so it turns out it's easier said than done. So I say easy, it's just possible, okay? So there's my first, and the second one looks kind of awful. And it kind of is, but there it is. There's the second one. And I claim it's linearly independent. How do I know that? Well, you've got an exponential here and something else here. It looks like pretty good chances that it's going to be a linearly independent solution or two linearly independent solutions. But now, that's the solution to the ODE. It's not a solution to the problem. How do I find a solution to the problem? Well, you have to find the values of these unknown coefficients, C0, C1. Actually, that is not impossible to do. So if I use the boundary conditions, which were y of minus 1 is equal to 1, and y of plus 1 is equal to 2, then I can find these coefficients. The coefficients depend on this function I, and it's actually through this interaction here, where I of epsilon is equal to this integral. Integral from minus 1 to 1, e to the minus 2s squared over 2 epsilon quantity. All right, this looks like a Gaussian integral, does it not? In fact, I can make it into a Gaussian integral and show that this is a Gaussian integral where I've subtracted off the tails, the so-called tails. All right, so here, that's what I'm going to do. I'm going to make it a Gaussian integral, a full Gaussian, and a full Gaussian means you're integrating from 0 to infinity. And this integrand, of course, it's a true Gaussian. It's an even function, even Gaussian. So really, I can write that when I write the Gaussian as 2 times the integral from 0 to infinity rather than the integral from minus infinity to plus infinity. And I'm going to subtract off 2 of the tails, but they happen to be symmetrics of each other. So I can subtract off minus 2 integral from 1 to infinity of that same Gaussian, rather than subtracting off that one plus the integral from minus infinity to minus 1. In other words, this guy here is a Gaussian integral with a small correction. how big was that small correction? Well, luckily, we did all that work in chapter 3, and we showed that this is a TST term. That's transcendentally small. So that was chapter 3. We showed the Gaussian integral works out to be square root 2 pi epsilon quantity plus a TST term because this integral is TST. So that's our truly small correction. So remember when we're calling something asymptotically small, it's a process. That means it's transcendentally small as something goes to infinity or something goes to 0. And the something is epsilon is going to 0. This implies, without too much work, that C0 is actually -1 plus a TST number. And you can show that from here. Why? Because let's look at this term here as well. What happens to this term as epsilon is going to 0? This term here is getting big. Epsilon to the minus big, really big, is TST. So TST plus something which is basically going to be something over epsilon, blah, 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 but not 0. And so I can just drop that term and call it a TST term. So C0 is just basically -1 plus a TST. A little bit of work involved, but not too much. What about this term here? In that case, a bit more is going to survive. And you can check that what's going to survive is going to be C1 equals 3 times the square root of epsilon over 2 pi plus a TST term. So that's what you get by analyzing this as epsilon gets smaller and smaller. So why am I doing this? Why am I hurting you this way? It's because we're going to ultimately take this limit and see what this function looks like. Okay, so that's what C0 is and C1 is this. So it's not hard to show that let's evaluate it at a couple points. So first of all, let's evaluate at the point x equals 0, where we said there's a boundary layer. So the boundary layer, we can show that as epsilon goes to 0, the boundary layer, or the value at the boundary layer, right at that boundary layer, x equals 0, is going to be 3 times the square root of epsilon over 2 pi plus TST. So this guy is going to where? What's its value? Depends on epsilon, but it's going to 0. And it's going to 0 with the power epsilon to the 1/2. Okay. Now let's take epsilon or x to be negative but fixed. Doesn't matter what value you take. Just suppose that x is some fixed number away from 0, but negative. Okay. So something less than 0 fixed. Then you can show that y through our limiting process is going to tend to -x plus a TST term. Let's take x positive. We can show then that y is tending towards 2x plus a TST term. So here's the picture. So on this branch over here, we have something which is looking like -x. Okay. And here we have something which is looking like 2x. And right in the center at 0, we have something which is going down to 0. Basically, this point is collapsing down to 0. So this tells us what the solution looks like. And I'll exhibit the solution in a little bit. You can actually put this solution into Mathematica with these constants, and Mathematica will plot that thing. And that's because it knows what the error function is. Okay, this looks like an error function or pieces of an error function. So it'll plot, and the plot looks like this. I probably have this on the next slide and forgot. Looks something like that. This is a boundary layer which is a bit different than any of the boundary layers we've seen before. And first of all, we've never had a boundary layer problem. Well, we had one, and that was in chapter 1. We haven't had boundary layers where we've had boundary layers in the middle, that again, going back to chapter 1, but this is something different because in that case, the two outer solutions didn't meet. Here, we're going to show that the two outer solutions, which is going to be this piece right here and this piece right here, actually meet in the middle. They meet in such a way as the outer solutions form a continuous function. Okay, that seems nice, but that cannot be, such a solution cannot be the solution to my ODE, right? Because that has a kink in it. It's not even differentiable classically one time. It's a function which is continuous, but not C1. So what happens in this case is you have the two outer solutions meeting, and meeting in such a way that the outer solutions form a kind of continuous function. And what happens here is, in this case, the solution forms what's called a corner layer instead of a boundary layer. Corner layer means your two outer solutions will meet, kind of shake hands, but do so in such a way that they meet in a non-C1 way. So that the solution is going to have to be some sort of rounding of that, and the rounding gives rise to what's called a corner layer. See, yeah, there's a picture of it. So in fact, in this case, I guess I lied. I didn't actually plot the true solution, but the true solution, if you take my word for it, would really be something like that. Right? And of course, we know what the limiting solution is going to look like. The limiting solution is when the outer solutions meet, and that's going to be the actual square cornered looking thing. Okay. Now what I'm showing here are composite solutions for different values of epsilon. So these are only approximate solutions. I didn't plot the true solution, but you ultimately can. You can force Mathematica to do that. I thought that I did, but I must have got tired one night and didn't do it. Anyway, this is pretty good approximation of what solutions look like, given to us from composite solutions, which we're going to generate from matched asymptotic expansions. We haven't done that yet, so let's do that next. That's where the cool part comes in. So here's our next example. We're going to consider exactly the same problem, but instead of going for an analytic solution, let's go for a matched asymptotic solution. Question.
Is there a reason why the right-hand side has a higher intercept or higher initial value than the left-hand side, or is it just a choice of the problem?
Yeah, it's just a choice of the problem. So remember, the boundary conditions were not sort of symmetric. In this case, the boundary condition is at y or x equals -1 has y equals 1, and this one it's 2. So if I choose the boundary condition where this is equal to 1, then there'll be exactly the same slope. Okay. Now we know that the outer solution is going to have this form, it turns out, C0 times x. So the C0 is dictated by the boundary condition. And this guy is going to be the boundary condition in both layers, but both outer solution regions. And the only unknown parameter there is C0. That can only be dictated by the boundary condition at this end and this end. So to answer your question, if I make this boundary condition 1, then my outer solution looks like that, and you get perfect symmetry, reflectional symmetry. Other questions? And by the way, if I choose my boundary condition to be, what if I chose my boundary condition to be -1 down here? What do you think it's going to happen? There's going to be no corner layer. Okay, so it is possible that you have no corner layer at all. And you can show that pretty easily. Then in that case, the solution to the whole ODE, it's not hard to show. In that case, the solution would be exactly -x. And all that complicated extra business is all 0, because in that case, C1 works out to be exactly 0, and this becomes a -1. Okay, so sometimes you can luck out, or you can, I don't know if you call it luck, but sometimes the boundary or corner layer never forms. Other questions? So let me erase that because that's a little misleading. All right, so now let's do, I guess, the reason why we do matched asymptotic expansions is because we usually can't get an analytical solution to compare against. But this one is still demonstrative and shows that interesting things can happen whenever we have our P function being or having a simple 0 in the domain. Now, if I change this, by the way, to say, okay, let's make P of x equal to x plus 2, then nothing bad ever happens. And in fact, well, I should say the only bad thing that happens is the regular bad thing, which means you have a boundary layer at the left-hand endpoint. Okay, but you never get a boundary layer in the center and all this extra stuff. Now, you'll see that not only does a boundary layer occur, and I'm calling the boundary layer the corner layer because generically you don't know if it's going to be a boundary layer or corner layer. Our boundary phenomenon is going to happen in the middle. And in this case, so that's one weird thing that happens. The second weird thing is that we can't do our regular matching procedure. It doesn't kind of go smoothly. And that's because the scale of our asymptotic expansion for the outer problem and the inner problem are two different things. So this will be the first time that's ever happened to us. So let's get started on this after I take a drink of water. So we're going to consider the same problem, same boundary condition, but we're going to do our usual matched asymptotic expansion method. And I'm not going to label everything in steps anymore because I think you all see what's happening. We can just go at this a little bit more quickly. So for our outer problem, let's assume that this is our outer expansion. We'll see that actually it doesn't matter that this is our outer expansion. We could do, instead of integral powers of epsilon, we could do half integral powers, and we're going to get more or less the same thing, as you'll see. We're going to assume that the outer solution is expansion in now 2 regions because there are going to be 2 outer solution regions. That's because our problem looks like this now. So in the middle, we're going to have a boundary layer. Outside of that, we have 2 outer problems, or 2 outer regions. So the one near the left boundary point and the one near the right boundary point. So we're going to have to do matching in 2 different zones, this zone and that zone. So let's see how this goes. Well, first of all, I want to assume that my outer solution is valid of this form in this zone and this zone. Now, when I say outer solution, that might mean that these functions that I compute in this zone are different than the functions that I compute for this zone. Or in other words, another way I can say this is I can define these functions that appear in this expansion case by case. I can define, or piece by piece, I can define it having a piece here and having a piece here. And that's what I'm going to choose to do. Now, I'm going to call my outer solution region, or my outer solution domain, -1 to x1 minus. That's x1 minus is that point there. And x1 plus to 1. So that's going to be that point up to that point. Where x1 minus is between -1 and 0. Doesn't really matter where it is. And similarly, x1 plus is going to be between 0 and 1. So just some point over here. Of course, this point here is x equals 0. Now, let's do a leading order. Let's compute our leading order problem for this outer solution region. And we get this equation if we do that. x times, remember the outer solution problem always looks the same. Basically, you just set epsilon to 0 and you replace the solution of the differential equation by y0. Okay, so x y0 prime minus y0 equals 0 for all x in the outer solution domain. Now we have two boundary conditions, right? And so we're going to apply both of them to compute a y0 function, which has two different values in the two different regions of my outer solution zone. So y of 0 is going to be minus x, big surprise, right? In the left-hand side, left-hand outer region, and it's going to be 2x in the right-hand outer region. Again, another big surprise, right? We probably could have guessed those by computing our exact solution and doing the analysis that we've already done. But now something interesting also happens. Because these are both linear in x, we can show that to all other orders, to all orders k bigger than 1, little yk is equal to 0 in the outer solution regions. That's kind of an interesting feature. So that means that y1 is 0, y2 also 0. So this is the asymptotic approximation to all orders, right? There's nothing else to add. Now, interestingly, you see, and this is why we have a corner layer, there's no pointwise jump in the solution when we continue this solution into where we expect the boundary layer to occur at x equals 0. If we continue it in, this kind of defies what we're allowed to do, but it's also important because it's going to tell us the structure of our problem. If we continue it in, keep going all the way to the boundary layer, we can see that this thing joins up in a continuous way, but not a C1 or C2 way. So we're going to get a boundary or a corner layer for this problem, not a boundary layer. Boundary layer means that a boundary layer would be in effect if we have the two solutions in the outer regions not meeting up continuously at the boundary layer. So in that case, we would have to have a solution, an asymptotic solution, which looks something like that. Okay, it would have to have a lot more interesting curvature going on. This doesn't happen, and so we get a corner layer. All right, now in this case, we don't know what the boundary layer thickness is because our theorem doesn't apply. Our theorem, actually I called it a proposition, only applies if P is everywhere positive on the domain or everywhere negative on the domain. Here it's not. So what we're going to do is we're going to introduce a stretch variable z, as we do usually when we're working in the blind, that is x over delta, and we have to choose that delta scale. So we have to use the principle of dominant balance. We're also going to define a new variable y as usual, and that's going to be defined as little y of z delta, replacing x with z delta. Okay, now normally if we don't know where the boundary layer is, we're going to subtract off the unknown boundary layer location, which we've been calling zeta. But here we know that the boundary layer is going to be at zeta equals 0, so that's why there's nothing else there. The ODE transforms when we make that rescaling like this. And now we're going to use principle of dominant balance. So when we use principle of dominant balance, what do we get? Let's see here. Do I have an error? So let's go back a second. What was our original? Oh gosh, that's going to be too far back. So there's our initial problem. So this one should be epsilon over delta squared. So when I replace x with this, so we should get what? We should get z delta, okay, over delta. Z delta over delta. So the deltas cancel. So it is okay. I was thinking I should have a delta appearing here, but no delta. That's because I have delta over delta cancellation. So now when we try to do dominant balance, we have to choose epsilon to the 1/2 power. So this is different than before. We've never seen this case, I don't think, before. And in this case, instead of the two terms, let's say the first two dominating the third, we actually get all terms being exactly the same order, which is allowed. So dominant balance, you're allowed to balance all terms when you choose a delta scale. In some cases that happens. You can't dominate one of the other terms. You simply have to agree to agree. So that's what happens in this case, and the inner problem transforms like this. But that's a problem, right? Because usually we have an epsilon that falls away in our leading order term. Here it doesn't happen, right? When we set epsilon to 0, nothing happens. There is no epsilon which appears. So what do? Well, we're going to have a second order problem, no problem there. Whenever we go to compute our inner expansion. But we don't have an epsilon, so how do we know what scale to choose for our inner expansion? Do we use integral powers of epsilon? Do we do powers to epsilon divided by 3? K over 3, K over 4. So it turns out it's not clear, but let's make a guess. And the guess is going to be based on the fact that our boundary layer thickness is order epsilon to the 1/2. So let's choose half integral powers of epsilon for our scale. Okay, half integral powers. Why? Because I don't know what else to choose. We could try K over 4, but this one actually works out. And I'm guided here. There's no guidance here from the equation. Usually there's an epsilon here, and that tells us, oh, you should use an epsilon when you do your expansion, integral powers of epsilon. Here, there's no such thing, so we don't know what to do. All right, here's another cool thing. All of the equations for all orders come out to be exactly the same. And it wouldn't matter if we choose, no matter what scale we choose for this, it doesn't matter. All of them are going to be the same because there's no epsilon which appears explicitly here. Nothing to do. We always get this equation. Okay. Well, what's the solution to this equation? The solution to this equation is exactly the same as the solution to the original equation, right? If you look at it, you've saved nothing. There's no savings here. The only thing you saved is you lost an epsilon that was originally there. The structure of the solution is going to be the same because that was always just going to be a coefficient which appears anyway, a parameter. So nothing's different. So there's our inner expansion. In fact, this is the same expansion for every at every order. So Y0 has this structure, capital Y0. Y1 also solves exactly the same equation. You just have different free parameters, 2 free parameters in each one. All the terms have exactly that form. Okay, and interestingly, they don't depend on any of the previous solutions like as usual. That's because there's no recursive nature in this expansion because our problem doesn't have any epsilon in it, like it usually does. Okay, so this is the solution to all orders. The only thing you change about the different orders is you're going to use different coefficients here. All right, let's perform the matching for the leading order case and see what happens. So because our boundary layer is at zeta equals 0, or our corner layer in this case, this is what we're going to set as the intermediate variable. But the difference here is that you need to keep this in mind. Both z and w could be positive and negative, not simultaneously, obviously, but could be positive or negative. That's because the boundary layer exists on both sides of x and z equals 0. Delta is equal to epsilon to the 1/2. Eta is some scale which sits in the middle of order 1 and order epsilon to the 1/2 power. W can be positive or negative. In the usual process, our powers are, or our asymptotic sequence is going to be epsilon. This should say, that's a typo, that should say K over 2, not 1/2. All right, so let's try the standard procedure. Let's try to match n equals 0, m equals 0, and we'll find actually we fail. So if we try to match that one, what do we get? So we get for the outer solution case, as usual, we replace x with w times eta. We expect to get the outer solution match function plus an order 1 term. And same with the inner. If we replace z by w eta over delta, we know what delta is. It's epsilon to the 1/2 power. We get, or should get, the inner match function 0, 0 plus an order 1 term. W, in this case, can be fixed and finite, but it can be both positive or negative. And critically, W is not equal to 0. Okay, normally it's just positive. Now it could be positive or negative, and I'll signify that it can be positive or negative, but not 0, as the absolute value should be greater than 0. All right, now here's the leading order solution when I replace x with w eta. Nothing to expand here, okay, because it's already in integral powers of epsilon and etas. Here it's just eta. So this is the match function. And since y of k is equal to 0, this is always going to be the match function to all orders. Nothing's ever going to change. Okay, that's always going to be the outer match function. It's always just going to be this guy. Notice there's no little o of 1 because I didn't have to do an expansion. Okay. So that is to all orders the match function. I'm always going to have to be marrying myself to that guy. Another way you can see it is any higher order terms are all zeros. So 0 epsilon, 0 eta epsilon, 0 epsilon squared, blah, blah, blah. Now, what about the outer solution or the inner solution? So for that one, we replace z with w eta over epsilon to the 1/2 power. And we get an expansion which looks like this. Well, what do we keep? It turns out the only thing we're going to be allowed to keep is going to be this guy. And we have to do this one in pieces. So the first piece, we have to assume w is less than 0. And then we're going to come back and do w greater than 0. Well, this piece, the only thing that's going to survive is this term here, because this is going to be transcendentally small. And because w is negative, when eta and epsilon get small, as they do, this is also going to turn out to be transcendentally small, because this number here is going to be on the left side of 0. So transcendentally small, there's my transcendentally small term. So it's only this guy that we're going to match. So that's the term we get. And we can't do anything about that because an epsilon to the 1/2 appears in the basement. Nothing else to cancel. There's no expansion we can do. It's already an integral power. Just so happens that the integral power is eta epsilon to the -1/2 power. Can we match that to the 0, 0 over here? No. Match not possible. Matching is impossible for n equals 0, m equals 0. So what do we have to do? We have to go to n equals 0, m equals 1. So that's where we're going to obtain a match. But time is unfortunately up, so we'll come back. I thought I was going to finish early, and I didn't even finish on time. So these slides are online. I think I posted them to Canvas. You can go look them up now, and you can also look at this in the lecture notes if you're really curious to see what happens. But otherwise, if you're not curious, you'll find out next time. So see you guys on Tuesday. Have a nice day.